Hello, this is Dr. Flight, and this is a video discussion that focuses on different assumptions that we need to help maintain and continue to think about as we're doing multiple regression in multivariate analysis. So there are some certain elements that we know we need to keep a check on linearity. So linear relationships, though we can adapt for that in the model, we look for that to begin with. Constant variance of error terms would be a error in heteroscedasticity. Where error terms grow over time. Error grows over time between two variables. Or variance grows over time, not error. So it's a heteroscedasticity issue. Independence of error terms, so that'd be a collinearity issue, and then normality in the error term distributions. So there's not a systematic error going on, but things are normally distributed. So we test our assumptions individually as we're looking at our data to begin with, and sometimes we can correct for nonlinear or non-normally distributed data by transformations. So we'll continue to look for transformation opportunities if there's nonlinear data. We could create some summated scores or composite scores, though, also, which helps our issue with non-normality as well. So there's a couple tools that we have to our use or advantage that we could be using to help control for non-normality. The other thing is, as we approach a large sample size, normality tends to emerge. So we want to test for independent variables and individual variables in both the dependent and independent variable side of the variate. And we also want to take a graphical approach as well. And then we want to be able to see if we can't make some transformations or try to normalize the data if possible. So linearity, homoscedasticity, which we want to make sure is their non-correlated error terms. And linearity is something to look for. The things we spend a lot of time in the analysis doing is just checking normality and then verifying or addressing issues of multicollinearity. So when independent variables share variance, when they correlate together a lot, then we lose interpretation, our ability to interpret the relative importance of those independent variables. So restrictions that we might think about in multiple regression would include this idea that we have to have linearity in the parameters that we're trying to measure, so linearity in the betas, perhaps, but also we think that independent variables are independent of each other, so there's not collinearity taking place. So that's something that we can certainly focus on and think of where independent variables are not linearly related to each other, and that the multicollinearity issue is resolved. The assumption that we make when we create a model theoretically is that the model accurately represents reality or some true underlying process. So this is actually a super important concept, that we're not just fishing for a variate that is statistically sound. We want one that is theoretically and from a practice perspective true. So reality is, certain phenomenon create and affect other phenomenon. We want to be able to model that accurately. We want to create an accurate model. So the assumption is that the model that we're testing is a model of reality, and we want to confirm that is really what we want to do. So so that's an important concept, that the model being fit to the data is a correct or valid representation of an underlying process. That should be remembered above everything else that we do, to be perfectly frank. So we do need to make sure that we have a large enough sample size. If we have a large number of Y values, or predictors, we need to have more than ample sample size to be able to find the power needed to predict Y. And also an assumption here is that when we fit the model will be true. So we assume that the model is accurate, and we find the residual values to indicate where there's inaccuracy in the model itself. So our task then is to assess multicollinearity issues and normality issues, because those are the two things we're thinking about. Normality, making sure that the relationships are linear and that they meet normality issues in terms of the independent variables, or the variables themselves, and that multicollinearity doesn't exist. And if it does, we want to try to interpret the results or its impact on our results. And then we also want to try to correct for it as needed. So that will be our biggest challenge here, is to think about this whole multicollinearity issue. The first thing that you should want to do is do a correlation matrix with the independent variables. I mean, that's basically what we want to do. You can also include the dependent variable if you want, but the bottom line is independent variables should not be highly correlated. They are going to be correlated some. Yep, no problem with that, but they shouldn't be perfectly correlated. Here's an example. If you have a correlation of greater than 0.9 between two independent variables, why use both variables? Just choose one of the two, because they both basically are they're sharing the same variance. So use the variable that is theoretically most plausible, and go with one instead of both. So again, if you have high correlation, then you have multicollinearity that will take place within your data set. So there's actually two things, something called tolerance and something called a variance inflation factor, the VIF. Now, we're not going to need to calculate this by hand, but the software that we use will. We will use what we call the variance inflation factor to suggest which variables don't contribute, along with tolerance, they don't contribute a lot to R square, but they do share variance with other values. So so this is going to be the rule here, and we're actually going to use this VIF, not the mean VIF. When we calculate VIF, the benchmark's going to be 10. So we want, if there's anything above 10, then that's a problem. And then when we have an R squared, 0.9 is super high. Even things like 0.7, 0.8, those R's are going to be difficult. It's really an R when we're talking about correlation between variables. So we're going to take that square out of there, because I'm not sure it should be there. I might have gone just crazy by adding a square that didn't need to be there. But the bottom line here is that when we have a high correlation, then that's a problem. You know, that R square might have been talking about the partial R square or partial correlation. and that may be something else that we can look at. But just look at the VIF, look at the correlation, and also the tolerance, which is described down here. So tolerance is the amount of variance in independent variable in an independent variable that's not explained by other independent variables. So when we actually do a printout, when we do a printout here, or when we run this, we'll see 0.10 as a cutoff value, and we want things to be above 0.10 here. But with the VIF, it needs to be below 10. So when we do our multicollinearity tests in SPSS and in, just in our statistical software, these two data points will actually come up. So we'll get a measure for tolerance, and maybe it'll be like 0.06. Okay, that's good. Because we don't, or excuse me, no, we want it to be, well, yeah, no, that's right. We want it to be below this. I'm doing this craziness here. Okay, so typically 0.10 would be the minimum cutoff. So tolerances that are below 0.10 are a problem. So if we have 0.19, then we're good. And then actually 1 divided by 0.19 is the variance inflation factor. So if we divided that, if we had 1 divided by our tolerance, it'll be our VIF. Okay, so these guys, tolerance and VIF, are related. If we want something above 0.10 for tolerance, it needs to be below 10 for VIF. All right, so that's just kind of a quick demonstration or discussion here of multicollinearity tests. Just like our other things we test for when we look at like skewness and kurtosis and just the shape, overall shape of a curve and those types of things, the range, look for outliers and missing data and all that other stuff in our data. We also look for multicollinearity among independent variables. So so again, correlation coefficients measure multicollinearity between pairs of variables. VIF measures the multicollinearity between independent variables and all of the other independent variables as a group. So it's a more powerful test than a simple correlation. And so we just need to be cautious and careful about how we view our variables. And every time we add add or delete an independent variable, it's going to impact our square or overall fit. And it'll also impact the power of the test as well, because we're messing around with our degrees of freedom at that point as well. So again, these are assumptions that we look at when we do multivariate or multivariable regression analysis. All right, so thanks for listening. Hope you enjoyed. The best thing to do here, to be honest, is probably run a few data sets. So, if you have data available to you, go ahead and test some regressions, look for multicollinearity issues, look for normality, and see if you can't increase the fit of your regression by modifying those independent variables that you have.